Hi everyone, Dave here again. This little mini lecture's on the types of hydrocarbons that you encounter in organic chemistry. Just before I start this, I just want to point out to you that there's literally millions of different kinds of organic chemicals, but they're divided up into groups, and probably the simplest group is those called the hydrocarbons, which contain only carbon and hydrogen. So by definition, therefore, they are organic chemicals, but they only contain those two elements. Organic chemicals, of course, can contain more than just hydrogen and carbon, but within the scope of TPP, we won't have time to have a look at these. Alright, so I've already talked about this. What's a hydrocarbon? It's the general name to those organic compounds which contain only carbon and hydrogen atoms. However, within the hydrocarbons themselves, you can basically regard them as being divided into three families, and these are the families that we're going to look at today. Just for your interest as well, I'll point out to you that there's another group, a major group in organic chemistry called the aromatic hydrocarbons, and again we won't be covering these either because it just doesn't fit into the scope of TPP. So the stuff that we're going to look at, these are called the aliphatic hydrocarbons. If you don't understand what I'm talking about, don't worry about it. It's just that if you come across it in your readings, it'll make a little bit more sense to you. Okay, what are the three families of hydrocarbons that we are actually interested in and which constitute the three major groups in the hydrocarbons? Well, the first one, which I guess arguably is the simplest group of the lot, are called the alkanes, and that's where all the carbon-carbon bonds within that within molecules within that family, they're all single bonds. There's also the alkenes. Now these are compounds where there's at least one carbon-carbon bond that's actually a double bond. So if you see if you're looking at a particular group and they're referred to as alkenes, you know that it's going to have a carbon-carbon double bond in it, and I'll talk about that a little bit more later on. And the next one is the alkynes. That's where there's at least one carbon-carbon bond that's a triple bond. So there we have it. We have the alkanes, the alkenes, and the alkynes, and I'm just going to look at these in a little bit more detail. Okay, let's look at the alkanes to start with. The way in which you systematically think about these groups of compounds is you think about the number of carbon atoms that they have. So, for example, here, if we just get my pen, there we go. The simplest alkane possible is where there is only one carbon atom. There it is there, and what's it look like? Well, it looks like that, if you like, or when you're looking at the molecular formula, of course, it looks like that. Why? Because it's going to have 4 hydrogens, because carbon has a valence of 4. And in organic chemistry, I guess you could say that the hydrogens they're a little bit like filler atoms. They're there to make sure that the valence of carbon at valence 4 is actually satisfied. So that's the simplest alkane, and arguably it's the simplest hydrocarbon that you can possibly get. That's methane. What is it? It's actually marsh gas, if you've ever heard of that term, and it's the same stuff that's actually produced in garbage dumps, and some people now actually drill into their garbage dump and actually use the methane as an energy source. Okay, the next one, carbon atom number 2, or sorry, I should say something that has 2 carbon atoms. The name of that thing is ethane. That's what it looks like there. You've got 2 carbons joined together, there they are, and as always you kind of fill in with hydrogens here. Next one's propane, and anyway you get the picture. I'm sure you can look at these later. I've just put in here, in some cases you come across these in everyday life. Propane, that's the major component in LPG gas, and butane is what you find in cigarette lighters. And you can see they've got quite straightforward shapes here. Now, to talk about particular hydrocarbons, as I said, you have to give them a name of some description, right? So the names are based on these prefixes, and I want you to remember the first 5 names. So it's methane, meth, eth, prop, bute, pent, and you'll see why remembering the prefixes is useful when we look at the other types of hydrocarbons. Just point this out to you as well, that there's a general formula for hydrocarbons, CnH2n plus 2. What this means is, if n equals 1, then if you put 1 into the equation there, I've lost my pen. Let's go back to here. If you put 1 in the equation here for n, that's 2 1s are 2, plus 2 is 4. So when n equals 1, h equals 4. There it is there. When n equals 1, h equals 4. Look at the next one. When n equals 2, 2 2s are 4 and 2 is 6. So the general formula for the next organic compound, the next alkane here, will be C2H6. There it is. So you can see how this general formula is consistent with the formula here for the particular alkanes. Okay, the other thing that I want to point out to you, and I think is important, is this one, is that the major force that actually holds these alkanes together, that is the molecules, are going to be van der Waals forces. Now, I've already talked about van der Waals forces previously, and I'm not going to go through all of it right now, but I just want to point out to you that you should be able to explain what van der Waals forces are, but also then relate particular phenomenon to the or the formula for particular compounds. So let me illustrate this by example. If I have a molecule that's, say, this big, and then another molecule that's this big, you know that those van der Waals forces occur because of slight changes in the electron clouds here, which lead to distortions in other electron clouds, and then some sort of attractive force between molecules. Now, what this means is, the bigger the molecules, let me draw a great big one here, or in fact 2 of them, the bigger the molecules, the bigger the van der Waals forces between them. In other words, the bigger the molecules are, the stickier they are. So as you go up from carbon number 1 to 2 to 3 to 4, etc., for the alkanes, the molecules actually stick together better and better because the van der Waals forces are stronger. So what that means is, for a compound like propane, that's the stuff in LPG gas cylinders, you need quite a big, thick metal container to contain the propane, because it actually produces quite a lot of pressure, because the particles between the, the forces between the molecules aren't that strong. But if you go up to the next number of carbons here, so going from 3 to 4, for butane, it's that little bit stickier. And so what that means is the van der Waals forces being a little bit higher between the butane molecules. That means that the pressure of the gas in the container isn't so high, because the gas particles are actually sticking together a little bit better. So you don't need anything like an LPG gas cylinder type thickness to hold butane liquid and gas under pressure. In fact, all you need is plastic, and that's why butane is actually used in cigarette lighters. So what I'm saying to you here is, you should be able to explain that rationale there, pretty much the way I've just explained it. Alright, we can keep going up in carbon number. I'll just give you a more extreme example. For things like waxes, they're essentially big molecules of hydrocarbon. They're a little bit more complicated than that, but I don't want to go into that. It doesn't really matter. The fact is, they're essentially big, long molecules of hydrocarbon. And of course, then the van der Waals forces between those molecules are very, very strong, so it's not so surprising that waxes are actually solids at room temperature. Of course, it also means that because it's only van der Waals forces that are holding those molecules together, the forces between them can allow the molecules to slip and then stick and slip and stick. So those kind of molecules are fairly slippery. So it's not surprising that waxes feel greasy or slippery to the touch. And again, you should be able to explain all that. Okay, we'll get on to the next group. They're the alkenes. As I've said before, the alkenes, they contain a carbon-carbon double bond. The simplest one this time is ethene. It can't be methane, of course, because methane would have only one carbon, and these things obviously have carbon-carbon bonds, so therefore the simplest one must be ethene. And there's some structures there drawn for you. You can see that the naming convention now makes perfect sense here. So ethene, propene, butene, pentene, hexene. If you refer back to the prefixes for the alkanes, you'll see that that actually makes perfect sense. There we go, there's our little prefixes. Okay, the general formula for alkenes is slightly different, of course, to the alkanes. It's CN2N. So if you put any number in here, for example, n equals 2, 2 2s are 4, so the general formula, the formula for a compound that has 2 carbons, that's an alkene, must be C2H4, and there it is there, and etc, etc. Okay, the alkynes, as I said before, they have carbon-carbon triple bonds. The simplest alkyne is going to be this one, ethyne. Methane, ethane, yes, it's got 2 carbons, and of course the name changes to INE, hence ethyne here. So there's the structure of ethyne, and of course they just go up in a similar fashion. And you must remember the first 4 names of the alkynes: ethyne, propyne, butyne, pentyne. Now, you can also see here that the formula obviously is going to change again for these alkynes. So the formula this time is CnH2n-2. So for example, when n equals 2, 2 2s are 4 minus 2 equals 2. So the simplest formula for ethyne, well, the formula for ethyne must be C2H2. Okay. We're on to the next mini lecture, so I will see you in that one. Bye.